Bob, would you like to
So
introduce
tonight,
this evening's speaker?
yes, tonight's speaker is Adam Farson. Welcome back, Adam. We're delighted to have you back with us again. Adam is very well known in the amateur radio community. He's a communications engineer. He's really helped out so many of us, especially for me. Adam's on the IC 7610 reflector, and he's really shared a lot of knowledge with the community about SDR radios, and he's going to talk to us about it tonight. But just let me re-emphasize something that Kevin mentioned earlier, because I got a few emails from people who weren't able to make it tonight. And so I just want to stress that this program is going to be recorded. If you want to review it again, or you want to share it with your friends, you can go to the Madison DX Club website. That's madisondxclub.org, and that'll show you a link to our video presentations. So with that, Adam, please go ahead with your presentation.
Okay, first of all, a little background. Good afternoon, everybody. I'll give a little background on myself first. I'm retired. I've worked for nearly 40 years as a telecommunications engineer. I was educated at the University of Cape Town in South Africa. I got a bachelor's degree in electrical engineering in 1963. And my first job after that was at Racal in Pretoria, the capital of South Africa, where I worked on development of military and commercial VHF and HF radio equipment, including a VHF man pack for the military, HF man pack and mobile, both solid state for commercial customers. This was back in 1964. We were pioneers in the development of solid state HF radio equipment. I would say we brought out the world's first solid state HF mobile and man pack. And after I finished up at Racal, I spent 3 years at CERN as an RF engineer, and then went back into the telecom industry and worked there for 20 years. I changed my professional discipline from RF to satellite communications, and then wireline telephone exchange engineering. I worked on that for 25 years in all. My last employer was Siemens. I was with them for 20 years in Florida, Germany, and Japan, and I retired in 1999. I was first licensed in South Africa in 1962. My first call sign was ZS1 Zulu Golf, and apart from a lapse of several years from 1967 until 1976, I've been continuously licensed. At the present time, I have a station at my home. I have a 7610 driving a Yaesu Quadra amplifier. I also have a Yaesu FT710, excuse me, which I purchased because it's a direct sampling SDR, and I wanted to test it. And either radio will drive the Yaesu Quadra amplifier. My only antenna is a Cushcraft R8, which is physically down for the moment, pending completion of restoration of the roof of the west wing of my house. Within a few days, I hope to have the antenna back up again. I haven't been very active on HF lately because of propagation conditions. And I also am on 2-meter SSB to communicate with some friends of mine on the local net. So I spend more time, as far as ham radio is concerned, I spend more time in the technology than in the operating side of things. I have spent a lot of time testing radios, and I have a fairly comprehensive lab on my website, which is alphabravo4oscarjulia.com. There is a list of test reports on all the radios I've tested. And my test reports are very comprehensive. I cover a lot of ground. I do quite an assortment of receiver and transmitter tests. So I sort of expand on the work done by Rob Sherwood. And recently I've acquired equipment which allows me to do phase noise testing accurately on transmitters. So now with this, it started out with an invitation to give a presentation on SDR testing at the SDR Academy in Friedrichshafen in 2016. So then the AMSAT South Africa group, which is headed by an old friend of mine whom I've known since 1964, Hans ZS6 Alpha Kilo Victor, invited me to give the same presentation at the AMSAT Symposium last year. I reformatted the presentation to fit into their template, as you'll see from the title page, and otherwise the content is exactly the same. So with that, I'll start off the presentation. When we look at the performance issues of direct sampling SDR receivers, many of the standard tests for legacy or superhet receivers with a DSP backend are also applicable to direct sampling SDRs. By a direct sampling SDR, I mean an SDR in which the RF signal is passed through a preselector to an analog to digital converter or ADC. The output of the ADC is in the form of a digital bit stream, which is passed to a digital down converter with a numerically controlled oscillator or NCO. These functions are usually nowadays incorporated into an FPGA, a field programmable gate array. And the output of the FPGA is a baseband with a bandwidth corresponding to one channel. It can be an SSB channel or a CW channel, depending on the mode. And the channel bandwidth, the emission type, and various other parameters are set either hard-coded or set by the operator or both within the FPGA. So your standard receiver parameters, MDS, or minimum discernible signal, front-end IMD, detection filter parameters, bandwidth, shape factor, stop band attenuation, phase noise, AGT threshold, S-meter tracking, notch filter depth, noise reduction and noise blanket performance and so forth are applicable for an SDR receiver just as they are for a legacy receiver. The sensitivity and selectivity are the core parameters of all receivers. Excessive noise or excessive IMD limit the usable sensitivity and effective filter stop band attenuation. Where in the past we used to strive for brick wall filters, but the processing time across a filter will increase the latency, and a compromise has to be struck between filter performance and latency. There are certain SDR radios in which the latency is so extreme that CW operation can be quite seriously compromised. You can have latencies up to more than 100 milliseconds, which really inhibits CW operation. Now, issues that we run across in SDR testing. With the advent of fast, cost-effective ADCs, the direct sampling SDR has eclipsed its quadrature mixer predecessors, or homodyne SDRs, in which conventional mixers in a quadrature or IQ configuration downconvert the RF signal to a baseband or a zero IF. An example of this is the Elecraft K2. KX3, my mistake, KX3. These types of receiver suffer from the same disadvantages as a superhead with a finite IF, in that phase noise in the local oscillator, the tendency of the mixer to develop IMD, passive IMD and downstream selectivity filters and roofing filters. All these things pose limitations to the receiver performance. Now, in a direct sampling SDR, we have some new challenges for the test engineer. First of all, and this will shock and has shocked some of the people in the contesting and DX community, the popular number on which so many people tend to shop for radios, namely DR3, third order dynamic range, has no relevance as a performance metric in a direct sampling SDR, because it is not a constant. It increases with increasing test signal power, reaches a peak at about 10 dB below the point at which the ADC clips, and then drops rapidly. So this forces a completely different approach to IMD testing. You can derive third order dynamic range at a point where the input power to the receiver is at the noise floor, but the number is not going to be constant as the signal power increases. The traditional third order intercept is meaningless in a direct sampling SDR, because in an analog to digital converter, the IMD follows a quasi first order rather than a third order law. There is a little further down the presentation, I have a couple of charts which illustrate this. The transfer and IMD lines diverge and never intersect, so there's no intercept point as such. In a conventional receiver, IP3 is the convergence point of the transfer and IMD curves. I should have changed the color of the word curves. Sorry about that. I'll have to go in and change it. The only phase noise source in a direct sampling ADC is the a direct sampling receiver is the ADC clock. There's no local oscillator. The numerically controlled oscillator in the FPGA, or that part of the receiver called the decimator or digital down converter, doesn't contribute phase noise. So in the design of the receiver, it's essential to keep the phase noise of the crystal clock oscillator, which clocks the ADC, as low as possible. And it almost eliminates reciprocal mixing noise. The ADC clock's phase noise is independent of the received frequency, unlike a conventional local oscillator. A case in point is the early version of the IC7300, in which there was degradation of the reciprocal mixing noise due to the layout, the physical layout of the clock generator and various multipliers and dividers in the clock system. This caused a degradation in the noise floor when dithering, which I will cover further on, was activated. Later on in the product life of the 7300, ICOM uprevved the main board to eliminate this problem, and they were quite successful at it. They reduced the degradation from 10 dB to about a half a dB. In a properly designed direct sampling SDR, RMDR exceeds 100 dB. So even the very best crystal oscillators as test signal sources can degrade the measurement. And if necessary, a notch filter whose stop band is centered on the frequency, on the test frequency, can be placed in the signal path to reduce the phase noise of the test signal. When I test RMDR, I use very high quality Wenzel crystal oscillators with phase noise of about minus 160 dBc per hertz. That's 160 dB below the carrier, measured at a bandwidth of 1 hertz at an offset of 1 megahertz from the carrier. This is a typical reciprocal mixing test setup. We have the signal source, variable attenuator, the receiver, and a level meter. Nowadays I use a Ballantine 323, which is an RMS voltmeter, instead of the HV339A, which is a distortion analyzer. If you do use a band stop filter, the place to put it is here. Oh, sorry, before the variable attenuator. These just explaining that F0 is the output of the oscillator and delta F is the offset. The device under test is tuned to F0. The signal generator is tuned to F0 plus the delta F. And the RF input power required to raise the audio output by 3 dB is noted. The RMDR is the OCXO output minus the attenuation minus the receiver MDS. And you can convert that to phase noise by adding adding RMDR plus 10 times the log of the bandwidth, the channel bandwidth, with a negative sign. B is the detection bandwidth of the receiver under test, which for the RMDR test is pretty well always 500 hertz. Now these are the curves illustrating the third order intercept problem. With a legacy receiver, this is the transfer curve. In other words, output power versus input power. The output power flattens off, but if you project this line up, and then you have the IMD line, which has 3 times the slope of the transfer line, you'll get an intercept point. Now with a direct sampling receiver with an ADC, this is your transfer curve. It's linear first order until you hit the clipping point, the point where the output of the ADC is all ones, which is the maximum power that the ADC can accept before it saturates. then the ADC will flat top. At that point, your IMD curve just keeps on going and it folds back because the ADC stops. In effect, the ADC stops working. It stops working until you back off the input power so that you no longer get clipping. So in in tests where you have to get close to clipping, what I do is I reduce the input power by 1 dB, and this is called the -1 dBFS point. Now, there is an exception. Actually, there are two exceptions to the this rule of ADC clipping being the limiting factor of the receiver. Collins have developed, Collins are in fact manufacturing a direct sampling SDR airborne HF radio. The designator model number is HFS 2200. It incorporates a dual loop AGC where the RF amplifier ahead of the ADC, or the preamp if you like, has two stages, each of which is controlled by a separate AGC line. The first stage is controlled by a pickoff point at the end of the DSP chain, following the output of the FPGA. In other words, just after the selectivity, like as it's done in a conventional receiver. The second stage, its AGC is controlled by an RF detector at the input to the ADC, the analog to digital converter. And the relationship between these two is set up in such a fashion that if there's a strong out-of-channel or out-of-band signal, it'll pull down rather the secondary AGC line and reduce the gain of the second stage before the gain of the first stage is reduced. It's a form of delayed AGC with two stages. The idea here is to prevent the ADC from clipping, whilst at the same time avoiding degradation of the receiver noise figure by not pulling down the gain of the first stage or preamp stage. Generally speaking, an ADC requires, it has a poor noise figure, and it requires an amplifier ahead of it. There's an amplifier which is always in the signal path. It's called the ADC driver, and it can have a gain of 14 or 20 dB depending on implementation. And any additional amplifier placed ahead of it is what we commonly call the preamp. So if you take a radio like the 7610, its ADC driver has a gain of 20 dB, and there are two preamps as well. And even with the preamps turned off, you still get a decent noise figure. Typically, the MDS of 7610 with preamps off is around that's a 500 hertz bandwidth. It's around minus 130 dB or better, 130 dBm rather or better. So the point I'm trying to make here is that the third order intercept point is not given by the manufacturers as a performance parameter of a direct sampling SDR receiver. And this is one of the new ways of thinking in testing SDR receivers. You don't publish a third order intercept figure. Now here's the third order dynamic range problem. In a conventional receiver, this greenish line here is the relationship between third order dynamic range, and two-tone input power for an Elecraft K3. This is the third order dynamic range curve for a Perseus direct sampling SDR receiver, which is an Italian-made compact receiver, which requires a PC as a back end. It's basically only a part of the radio, if you like. It's the receiver up to the FPGA output, and the bit stream which comes out of that receiver is fed over a USB cable to a PC, which provides all the selectivity, signal management, and demodulation functions using software supplied with the receiver. You can see what happens here is direct sampling receiver. The third order dynamic range hits this peak or sweet spot and then drops rather rapidly. Now, the upshot of this is that you need to measure the IMD at over a fairly wide range of signals, from the maximum input that the receiver will accept down to the noise floor. This chart, which I've just put up, shows that the dynamic range of the third order dynamic range of a direct sampling receiver is unusable as a predictor of dynamic performance. It increases, reaches a sweet spot, and then falls off. By contrast, the third order dynamic range of a conventional or legacy receiver decreases as you increase the input power. So based on ideas put forward by Steve Hicks of Flex Radio, I took a concept that he had and elaborated it a little bit further. By specifying receiver IMD in terms of IFSS, or interference-free signal strength, what I do is this. I measure the absolute power of the IMD product in dBm against the two-tone input power and draw a chart with the ITUR recommendation P372 band noise levels for typical urban and rural sites at the frequency of operation as datum lines across the chart. So I call this an IFSS chart. If the interferer is below the band noise at the user site, the band noise will mask it and it will not be heard. So you don't have to worry about it operationally. The actual noise levels are, of course, site-specific, and the band noise levels shown by P372 are typical. You can derive DR3 at the noise floor by noting the per tone input power where the IFSS curve first crosses the DUT noise floor. Here's the test procedure for IFSS. I've dwelt on it because I'm putting it forward as an alternative to the conventional third order dynamic range number, with the caveat that this number should not be used as the analogy of the 0 to 100, the way I always put it, the 0 to 100 kilometer per hour time of a car. Because when you're buying a car and you buy it on your 0 to 100 kilometers an hour time, and you neglect the fact that it'll flip on the first curve it encounters, it's not a very good car. We measure the absolute amplitude of each interferer and draw the chart, which we'll see on the next slide. if the interferer is below the band noise, it can be disregarded. The IFSS method eliminates the sweet spot problem, which we've covered earlier. We can read the observed IMD product on a direct sampling SDR. Typically, you can read it on the spectrum scope or the S meter and place it on the chart. You know the input power because you measure the level of the two-tone signal going into the receiver with a power meter before you start running the tests. One essential tool, which I always use when doing this test, is a power meter such as an HP 437B, 432A, E4418, one of those microwave power meters with a sensor which is appropriate to the frequency range and power level in use. Once you check the scope and S-meter level calibration with the signal generator before taking these readings. So a good, reasonably well calibrated signal generator, actually two signal sources, are also a requirement for this test. I use two HP Agilent or Keysight signal generators, or a Keysight and the Rohde & Schwarz, depending on the frequency range I'm working with. I do the test with preamps off because a preamp will degrade the IMD. The AGC driver, the ADC driver, the analog to digital converter driver is always in place. You can't switch that off. Now, some direct sampling SDRs don't use an active driver. Typically, the active driver would be something like an LTC, Linear Technologies, LTC, I'm trying to think of the part numbers. LTC make a couple of them. I think 2641, something like that. Don't remember the number quite off the top of my head, but LTC make a couple of ADC driver chips, with one with 14 dB gain and one with 20 dB gain. Flex Radio is an example, and also Collins use a transformer ahead of the ADC. The transformer is nice in a way because it provides 6 dB of gain without adding noise. Its disadvantage is that it's subject to passive IMD on strong signals where the transformer core is driven into saturation. The IFSS curve is quasi-first order, as I mentioned, until nonlinearity in active stages ahead of the ADC introduces third-order effects. The active stages are the preamp, if it's in circuit, and the ADC driver. This is the test setup for measuring IMD in a receiver. I no longer have these Marconi generators. They've been replaced. When I did a lab upgrade, I replaced them with a Keysight or Agilent HP E4428C and E4432B. The generators are buffered. The purpose of these buffer amplifiers is to prevent the limited transhybrid loss of the combiner from allowing the signal from one generator to go back into the other generator and make IMD products. Each amplifier, these are all mini circuits components. Each amplifier is followed by a low-pass filter and an attenuator. This is a hybrid combiner built around ferrite transformers, ferrite core transformers. And then there's a variable attenuator, the receiver, and finally the RMS voltmeter measuring the audio level of the receiver. Now, another thing I wanted to mention incidentally in passing is superhet receivers that have a roofing filter after the mixer. The roofing filter has a disadvantage in that all crystal filters are subject to passive IMD, and under strong signal conditions, the roofing filter can degrade the linearity of the signal and undo the very benefit that it was supposed to confer. I ran across one situation testing a particular radio in which passive IMD in the transformers surrounding the first mixer ruined the performance of the receiver under strong signal conditions. It was quite a well-known make and model of transceiver. It's now been discontinued, not for that reason, but nevertheless, when I did that test, I was quite taken aback by the poor performance, because it had been advertised as a premium level contesting and DX receiver. Now, coming back to this test, the test signal power, whoops, bear with me. Sorry about that. The test signal power is adjusted for the desired IMD product level as read on the spectrum scope or S meter, or for a 3 dB increase in audio output level when testing second order dynamic range. And the adjustment is done by adjusting this attenuator. The point of second order dynamic range is to deal with IMD products generated by two strong signals which mix additively to throw an IMD product into an amateur band. An example would be 6.1 and 8.1 megahertz, which produce an IMD product at 14.2 megahertz. This is rather relevant in region 1, Europe, where there are strong HF broadcasting stations, which really mess up the 40-meter band at night. As I mentioned here, these buffer amplifiers keep the generators, the signals from the generators out of the opposite generator. Now, I mentioned the ITUR P372 band noise curves. These are the curves published in the ARRL handbook. Where you have residential or urban, rural, and quiet rural band noise curves. Now, these are the typical, not specific to any one site. They can be used as, they are used as a guideline. This is a typical IFSS curve for the Perseus receiver. We start out by applying a signal 1 dB below the clip level, and we gradually reduce the signal level, and we draw a curve of input level versus IMD product level. These horizontal lines here are the urban and rural noise floor curves, or lines rather. Now, you'll see I've mentioned dithering. Okay, the next question is, what is dithering? If a random noise component is added to the incoming signal in a suitable way, in a proper way, it decorrelates the IMD products. What it does is this noise added to the signal breaks up, if you want to put it this way, it breaks up the noise, breaks up the IMD products which are correlated, they're tones, into non-correlated noise. And the noise can be removed from the signal by a mathematical process if it's generated in a particular way. So an ADC with the built-in dithering feature generates the dithering noise by using an on-chip binary random sequence generator, in other words, a random pseudo noise generator, it's just called to generate a pseudo random bit sequence, or PRBS, which is mixed with the analog signals coming in at the input of the ADC. So this pseudo random noise is digitized, and because it's been mathematically generated on the ADC chip, it can be mathematically removed. So at the output of the ADC, there's another process which which applies the inverse of the digitized pseudo-random noise to the output bit stream coming out of the digitizer section of the ADC. So this noise is removed from the digital bit stream or payload coming out of the ADC, and therefore does not degrade the signal. It's a clever artifice which enables the designer to greatly reduce IMD products without compromising the overall performance of the ADC. You can see what dither does here is it smooths out variations in IMD level with changes in input amplitude. This is the IFSS curve of the ADC used in the Perseus without dither. And when dither is added, the curve is pushed down and made more monotonic. So the IMD performance of the receiver as a whole will be improved. Some ADCs don't have on-chip dither, so oh, excuse me a second. Hello? Friday. This Friday, the 13th. Okay, thanks, Dave. Bye. Sorry about that. The phone is on the same desk as my computer. And there's like I can't see the mute button. Okay. What the dithering does here is it smooths out this curve. So reducing the overall effect of IMD on the signal, therefore it increases the performance of the receiver with fairly little effort. Now there is one make of direct sampling SDR transceiver, Flex Radio. They use a very fast ADC because they cover 2 meters as well as HF and 6 meters. So they have to use an ADC which doesn't have the capability of on-chip dither. Instead of using noise for dithering, they use the third tone, and they have to custom adjust the frequency and amplitude of that tone for each individual radio to get the best performance. That's what they call that, their magic knobs. I prefer the noise method using a chip, an ADC chip with on-chip dither. Examples being the LTC 2208 from ADI, Analog Devices Incorporated, and the TI, the Texas Instruments ADCs. Also, some of them also have on-chip dither. Dither can be switched on and off in some radios. In others, it's on all the time. For example, in the Yaesu FT710, dither is on all the time. They don't. The Yaesu radio generates the dither in the FPGA, so it uses ADCs without on-chip dither. But the process of adding the dither and then removing it downstream is the same. The Yaesu appears to be using a licensed variant of the Collins dual AGC system. That's why I mentioned it. Now the popular ICOM radios, the 7610 rather, and the 7300 have ADCs with on-chip dithering, and they use this method. Here's some other considerations for HF SDR receiver testing. In a direct sampling SDR receiver, the concept of blocking is, in the conventional sense, has to be treated with caution. No blocking occurs until the ADC is driven into saturation or clipping. This assumes correct gain distribution. In other words, that the ADC must clip before active stages prior to the ADC start blocking. Clip level is measured and stated, clip level in dBm, rather than blocking dynamic range. The exception here again is the Yaesu FT710, which blocks somewhat gracefully, but it doesn't clip. The dual loop AGC ensures that the Yaesu radio cannot be driven into clipping. If you drive it up to about -2 dBm input, it'll start blocking. I mentioned second order IMD. Image rejection and IF leakage measurements are not applicable, but an aliasing rejection test is very useful. To test aliasing, you inject a signal, excuse me, in the second Nyquist zone. In the second Nyquist zone. In other words, the frequency of the test signal has to be higher than half the sampling rate, and you measure the amplitude of the product thrown into the first Nyquist zone. The lower aliasing product means that the anti-aliasing filter, which is a low-pass filter in the RF signal path, is better. Now, another new test which I introduced is the noise power ratio test. Those of you who've been in the telecommunications industry probably remember from the days of analog frequency division multiplex carrier systems that noise power ratio testing was used to assess the performance of multi-channel microwave and analog satellite communication systems. I started doing some research in 2010 or so to see whether noise power ratio testing could be applied to the testing of receivers. So, with the help of an Italian retired engineer who used to work for a telecom equipment manufacturer in Italy, I figured out how to use a notch noise generator, which is normally used for noise power ratio testing in the telecom industry, to test receivers. It's a stress test. The NPR test equipment consists of a noise generator and a noise receiver. What they do in the telecom industry is they apply a band of noise with a deep notch at the frequency of a particular channel in the system. And we're using the test receiver. They measure the amount of noise in that notched out channel. What will happen is the notch will remove the applied noise test signal or noise loading over the bandwidth of the test channel, and any noise appearing in the test channel is generated by impairments in the receiver. Well, in the telecom system, the carrier system, or in the case of a receiver, it would be unwanted noise in the receiver. You can use the system to test for passive IMD and a filter or other passive component by placing the filter in the signal path between the noise generator and noise receiver. It's quite useful in the development of things like preselectors. But when testing a receiver, a radio receiver, all you need is the noise generator. You apply the noise band or noise loading with a notch. Pardon me, something's going on here. Okay, what you do is these curves illustrate what goes on with a noise power ratio test. You apply the band of noise or noise loading, and you have a filter 90 dB deep or better at the frequency at which you wish to test. I reuse, in this equipment, which is recovered from telecom industry surplus, I use filters which are on the frequency of standard FDM carrier channels, some of which fall within amateur bands. This one is in the 60-meter band. So what we have here is the filter is goes all the way down to about 95 dB. And the difference between the noise shown on the radio spectrum scope and the actual filter stop band is noise caused when generated in the receiver when the noise loading mixes with phase noise in the receiver and causes IMD in the receiver. In other words, the degradation which the noise loading causes in the receiver raises the noise floor in the notch filter. And you see that here. So the higher the noise in the notch filter, the worse the receiver. You can generally assess the quality of the receiver by saying that if the NPR, the noise power ratio, which is the ratio of the noise in the notch to the noise in a bandwidth equal to that of the test channel outside the notch, is between, let's say, 70 and 85 dB, you've got a good receiver. If it's between 65 and 70 dB, the receiver is okay. If it's below 65 dB, I would say that's an indifferent receiver. This is a very powerful test, which unfortunately suffers from the disadvantage that the equipment, this type of equipment, the notch noise generator, is not readily available anymore because analog frequency division carrier systems have been out of service or out of favor for many years now. It's possible to do this test using an arbitrary waveform generator or a vector signal generator, but those instruments are very expensive. So here are some definitions for noise power ratio testing. Wideband Gaussian noise from the noise generator is applied to the receiver input. The noise loading provokes added noise in the receiver due to IMD and reciprocal mixing. The added noise power is a measure of the overall receiver performance. Less added noise means a better receiver. A perfect receiver will not add any noise. The notch filter, just wider than the receiver's detection bandwidth, is placed in the noise generator output. The notch needs to be better than 90 dB deep. The receiver is tuned to place the detection passband in the center of the notch. A bandpass filter ahead of the notch filter defines the applied noise bandwidth. Ideally, only the added noise generated by the receiver's impairments will appear in the detection passband. And you can see that on the radio spectrum scope. NPR is the noise power in a channel equal in bandwidth to the detection passband, but outside the notch, divided by the noise power in the detection passband. The theoretical maximum NPR can be calculated for a given ADC and used as a performance datum point. If the measured NPR is much worse than the theoretical NPR, this may indicate passive IMD in the front end, typically a transformer core or a filter going into saturation and generating IMD. Give you an idea of the noise power levels involved. In a typical NPR test, the noise loading is equivalent to about 1,200 contiguous SSB signals, each at 30 dB over S9. So it's a very stressful test for any receiver. This is an example of the type of noise generator that is used for this purpose. This is a German Bundle and Goldemann noise generator. These are the bandpass filters, and these are the notch filters or band stop filters. I got these filters by watching eBay carefully and just scrounging around until I found the set of filters I wanted. And I now have filters that cover 16 kilohertz to 16 megahertz. These are attenuators, various control switches. To perform the test, you apply the noise loading without the notch filter, and you set the level so that the receiver is 1 dB below clipping. Then you switch in the notch filter, and you read off the level of the noise generated in the notch from the spectrum scope. Another test that I would like to cover here is latency. The signal transit time from RF input to audio output in an SDR is a function of real-time processing power directly affected by DSP filter parameters. Latency is of critical performance in high-speed CW operation, especially full break-in, and also in digital modes. Latency greater than 100 milliseconds can also degrade voice operation, especially fast back and forth with Vox, and can render the monitor function almost unusable. A compromise has to be struck between filter shape factor and latency. Receiver latency is measured by applying a pulse train with fast rise time to the RF input and measuring the time interval between the applied pulse and the received pulse using a 2-channel oscilloscope. CW transmitter latency, the way I do it is I key the transmitter with bits and measure the time interval between the leading edge of the keying signal and that of the transmitted dit with the oscilloscope. Another method I use for SSB latency testing is to apply.
He sounds dreadfully boring.
Oh, he is.
Why don't you turn it off?
Oh, hi, Gerald.
Adrian, I'm sorry, you're going to have to unmute yourself. I got trigger happy and muted someone who was talking.
Yeah, just as I was saying here, I use a function generator to produce a 1-cycle burst of test tone, put it in the mic input, and measure the time interval between the leading edge of that burst and that of the transmitted signal. So the latency tests are fairly simple, and they yield usable results. These are shape factor and curves of shape factor versus latency, which I took on an Annan receiver some years ago. This is a low latency filter, and this is a linear phase filter, and this is the standard Power SDR version 3.3.7. This is quite a few years back. They've gone on to Annan have gone on to much more recent software now, but at the time I captured these curves and put them into this program. One final remark I wanted to make about the architecture of some of these radios. The DSP functions, with which we've become familiar over the years from hybrid superhead receivers, that is, receivers with a superhead front end, and DSP providing the downstream signal management, IF management, selectivity, demodulation, audio management, etc., including the notch filter. These are performed either in a separate DSP IC following the FPGA, or in the case of the IC 7610, the DSP functions are contained within the FPGA. And but either way, operationally they're the same. Anyway, this is the last slide in the presentation, apart from a set of references at the end. So well, I'll turn over the presentation to questions now. Please go ahead with any questions you might have.
Any questions, comments?
Question question that I have is, when did the IC 7300 change the board? Do you know by any chance?
Let me think about this. The radio was first released in 2016. I believe the change was made in 2018.
Any way to track the serial number? To see which, any way to figure out if you ever call it an old radio versus new radio?
Oh, I can't think of serial numbers off the top. Yeah, I'm trying to think about serial numbers. I can't really give you a guideline on that, but radios which were available at dealers in 2018 and afterwards, as far as I remember, had the improved board. This change was not announced.
Hey, thank you.
I just noticed on the Sherwood Engineering page, it mentions a second test of the 7300 starting with serial number 02001408, although that doesn't indicate whether that was the first one or not, but that's the first one they tested with the improvement, I think. I don't know. It's a guess.
I know I had an early 7300 and it had that issue. Then Rob acquired a second one, and he reran the test and noticed that the dithering hardly affected the noise floor. Now on the 7610, the change in noise floor when you activate dithering is less than a dB.
Adam, we have a question in the chat, and it is, at what point would any of these measurements actually impact our ability to hear better or worse?
Okay, well, if a radio has poor reciprocal mixing noise and there are strong out-of-channel signals, this will affect the ability to hear a weak signal, for sure. Because what will happen is that the phase noise of the clock, which is the main source of phase noise, will mix with the strong out-of-range signals to produce in-band noise products which can overwhelm a weak signal.